Hello friends, welcome to my new video. This video is all about the stability of the gravity dam. It is completely practical approach which include numerical problem. While you are watching this video means you have gone through the theory lectures of the gravity dam and forces acting on the gravity dam. So without wasting any time, let's begin with the analysis. Here we have to analyze the stability of the gravity dam by considering the self weight, head water pressure and uplift water pressure in full reservoir condition. Well, in order to analyze the stability, following steps have been manufactured for. Step 1 is the force identification, followed by the force calculation, lever arm calculation, moment calculation, eccentricity calculation, and then we have the safety checks, that is the factor of safety against tension, overturning and sliding. Later on we'll calculate the principal stress and the shear stress. On the left hand side you can see the typical diagram of the gravity dam. It includes the pressure diagrams also as well as the forces. So let's discuss and identify the forces. We'll first discuss about the forces due to the weight of the dam. Since the shape of the dam is irregular, so we have divided the section into uniform shapes. So two triangles and one rectangle. So W1 and W3, they are in triangle, and one in rectangle, W2. So these are the three forces due to the weight of the dam body. Now the weight forces due to the water, that is here PV1 and PV2 is acting on the dam body section W1. So these two will be the vertical forces acting on the dam section, PV1 and PV2. Next we are having the uplift pressure, PU, which is acting against the dam body. And last one is the head water pressure, PH. It is generally acting at a distance of h by 3 from the bottom or 2h by 3 from the top. So these all are the forces. And one more thing regarding the characteristic of the forces. So all those forces that are in the direction of the dam body, they are acting as a resisting forces, whereas those that are acting against or that makes the structure unstable are called overturning forces. So here head water pressure, pH, and uplift pressure, PU, they both are overturning forces. And we have categorized the forces into two categories, that is vertical forces and horizontal forces. You can see the table, how we have arranged the table. Now let us go for the force calculation. The first force, W1, that is the dam body, weight due to a force due to weight of the body. So W1 is a triangle, so normal trigonometric formula is applied over here, that is half base into height, and here gamma d is multiplied, means the specific weight of the dam material, that is here we have considered it as a 24 kilonewton per meter cube. So substituting the value, we will get almost 1860 kilonewton. And similarly W2 is a rectangle having a width of 7 meter and a height of 68 meter, the entire height of the dam section. Simple, x2 into hs into gamma d. So this will give us a value of around 11,424 kilonewton. And the third forces due to dam body is W3. It's a triangle having a height of h4, that is 54 meter, and a base of x1, that is 41 meter. So 1 by 2 base into height into gamma d. So this will give a force of 26,568 kilonewton. Now let us go for the forces due to water, that is PV1 and PV2. PV1 is in a triangle shape. Same formula as we have applied for the W1, but only the specific weight of water is applied over here, gamma W. So after substituting the value, we identified 775 kilonewton of force acting on the dam structure. And PV2 is in a rectangle shape having a height of h5, that is 34 meter, and a width of 5 meter, x3. So, and a specific weight of water. So substituting the value, we get a force of around 1700 kilonewton. The next one is the uplift pressure. Since uplift pressure is acting throughout the width of the dam section, that is B is equal to 53, and having a height of the HFL of the water, that is H6, 65 meter. So it is 1 by 2 B into H6 into gamma W. So substituting, we get around, since it is an overturning, so negative sign is applied over here, since it is acting against the dam forces. So 17,225 kilonewton uplift pressure is applied. And the next one is the pH. It is the horizontal pressure by the headwater, and it is applied generally at a height of h by 3 from the bottom or 2h by 3 from the top. So here we have applied from here. So here the formula for headwater is nothing but it is gamma W into h square by 2. Here h is nothing but it is h6, height of the water, HFL, 65 meter. So here also it's a overturning force, so negative sign is applied. So after substituting the value, we get around 21,125 kilonewton. And since it is placed in a horizontal force, because it is acting horizontal to the in a horizontal direction. So depending upon the characteristic of the force, they have been placed in vertical as well as in the horizontal forces. Now the calculation of lever arm. What is lever arm? Lever arm is nothing but it is the location of the resultant forces acting on the dam body, where the resultant force is acting, and resultant force is generally acting on the CG of the dam section. So every shape has different CG locations. So for triangle, either it will be lying 1/3 or 2/3 of the base width. So for calculating the lever arm for W1, we can go for a calculation either from toe or from the heel. Here in the analysis we have gone for from toe. So from toe, the resultant force acting on the W1 section will be x1 plus x2, and in this shape of the triangle, the CG is lying at a distance of 1 by 3 of the base. So 41 plus 7 plus 5 by 3. So you can see 41 plus 7 plus 5 into 1 by 3. We get this value. Similarly for the W2 is a rectangle, so CG will be at the center. So here the lever arm will be 41 plus x2 by 2. So 41 plus 7 into 1 by 2. Now for W3 is a triangle and we are standing in the acute angle direction. So here the CG will be at the distance of 2 by 3rd of x1. So 41 into 2 by 3. Now for PV1 is just above the W1 in a mirror image. So it will have a CG at a distance of 2 by 3rd of base. So similar calculation as that of a W1. So 41 plus x2 is a 7, and here it will be x3 into 2 by 3. So we get 41 plus 7 plus 5 into 2 by 3. And PV2 is a rectangle in shape. So CG will be lying at the center. So 41 plus 7 plus 5 by 2. 5 into 1 by 2. Now for uplift pressure, it's the pressure diagram is in a rectangle and the moment is taken from toe. So toe end is in acute angle. So here the location of the CG will be 2/3 of the base. So base of the section is B equal 53. So 53 into 2 by 3. Now the last one is a pH. Here also the pressure diagram is in rectangle in shape. So if you are calculating from the bottom, the lever arm will be at a distance of h by 3. 1 by 3. CG will be lying at a distance of 1 by 3. So height is 65 meter into 1 by 3. So 65 into 1 by 3. So here we get the lever arm for all the forces. Now we have to calculate the moments, the resisting moment as well as the overturning moments. So these are the two columns. So those forces that are having a nature of a resisting, they will go in the resisting moment, and those forces that are having the overturning characteristic, they will move to the overturning moment column. And it is nothing but it is the product of the lever arm into the force. So multiplying the force into the lever arm will get the moments. So we have find out all the moments resisting as well as the overturning. Now we have to sum the summation of all the forces as well as the moment, and this will be required for the further calculation. Now we will begin with the calculation of the eccentricity. Eccentricity is nothing but it is the location from the center of the base where the resultant force is acting. Here we have expression E is equals to B by 2 minus X bar. Here in a normal uniform shape, the eccentricity may be B by 2 for any rectangle shape. But here the diameter section is in irregular shape. So we have to identify the exact location of that resultant force. So the formula is something like this: B by 2 minus X bar, and X bar is nothing for which is the resultant force acting at a distance of center from the base, and B is nothing but it is the base width of the dam section, and X bar is calculated as an expression of summation of the resisting moment minus summation of the overturning moment divided by the total vertical forces. After putting the value, we find that X bar is nothing but it is 15.36 meter. So eccentricity will be around 11.14 meter. So we got the eccentricity 11.14 meter. Now let us begin with the first check, safety check. There is a factor of safety against tension. So condition 1 says that the eccentricity must be less than B by 6, and B by 6 is nothing but it is 53 by 6, that is 8.83 meter. It is 8.83 meter. But our eccentricity is more than 8.83, means the condition says that it is fail against tension. So for no tension to be developed, the eccentricity should be less than B by 6, or in other words, the resultant force should always lie within the middle third of the dam section. And some other points regarding the value of eccentricity. If the eccentricity is less than B by 6, then the base of the dam section experience compressive stress. Always remember this point. And if the eccentricity is greater than B by 6, means the dam base of the dam experience tensile stress. Means with respect to this statistics, you can say that the base of the dam section is experiencing the tension stress. Let us see the condition 2, that is the normal stress. And normal stress says that if the stress on the heel is less than 0, then the dam is not safe in tension. So let us find the normal stress in heel. So here we have expression, here we are having expression, that is, it is the summation of vertical forces to that of the base width into 1 plus or minus 6e by b. Here plus or minus says that plus is for toe condition and minus is for heel condition. So we will check for this condition. So heel is stress at heel is equals nothing but we get around minus of 123.92 Newton per meter square. Unit is Newton or kilonewton per meter square. So here it's negative, means less than 0, hence not safe. Means our dam section is not safe in tension. Now let us check the factor of safety against overturning. Here the first condition says that the ratio of the resisting moment to that of the overturning moment must be greater than 1.5. So let us substitute the value and find the ratio, and ratio is 1.36, which is less than 1.5, hence it is not okay. Once you find not okay over here, just go for second check in condition 2. It says that the summation of the resisting moment must be greater than the summation of overturning moment. This condition is satisfied because our resisting moment is more than the overturning moment, hence it is safe against overturning. Next factor of safety is against sliding. For sliding case we have one condition, that is the expression this, that is mu into summation of vertical forces plus base weight into q divided by summation of horizontal forces must be greater than 1.5. When we check this value, we find the value is more than 1.5, that is 4.34. Hence here we can say the dam section is safe against sliding. In this expression, the value of mu is ranging from 0.65 to 0.75, and in general case it is taken as 0.7, and q is nothing but it is 1400 kilonewton per meter square. So means our dam section is safe against overturning and sliding, but not safe against tension. Let us also calculate the principal stress and shear stress. It is nothing as compared to, we have already calculated the normal stress. So for principal stress, it is the product of the normal stress into sec square alpha 1. Here alpha 1 and alpha 2, they are the angles subtending at the toe as well as in the heel section. If we go and look the diagram, you can see at the toe alpha 1 is subtending and at the heel alpha 2 is subtending, and this value can be identified by the normal trigonometric formulation, that is nothing but tan of alpha 1 is opposite over adjacent, that is height into base, that is 54 by 41, and here tan alpha 2 is nothing but it is opposite over adjacent, that is h3 over x3, 31 over 5. With this formulation you can identify the value of alpha 1 and alpha 2. We have already calculated and we find the alpha 1 to be 52.8 degree and alpha 2 as 80 degree 84 minutes. Substituting all the values, we have calculated the principal stress as well as the shear stress. Hope you have enjoyed the video as well as you have learned how to do the safety analysis or the stability analysis of the gravity dam. Thank you. if you like and share the video.